What if I told you an architect from 500 years ago built something smarter than your iPhone? Meet Mimar Sinan, the Ottoman genius who embedded an earthquake survival code into Istanbul's skyline. While modern engineers use supercomputers, Sinan used stones, geometry, and secrets we're still scrambling to decode. By the end of this video, you'll see why Süleymaniye Mosque isn't just a building. It's a middle finger to tectonic plates. Lost power, Wi-Fi drops, smartphones say recalculating. We freak out when our gadgets fail. But imagine relying on gooey mud walls and hand-cut stone to survive quakes up to magnitude 7. Today's engineers scratch their heads at how the Süleymaniye, built between 1550 and 1557, still stands tall on Istanbul's third hill. Sinan didn't have steel rebar, high-strength concrete, or computer simulations, yet he designed a mosque that has weathered centuries of Ottoman earthquakes better than many modern renovations. Süleymaniye's foundation isn't anchored to solid ground, it's designed to float during quakes. Here's how Sinan hacked geology. Excavations revealed a 13-foot layer of charcoal beneath the mosque. This wasn't random. It absorbs moisture and acts like a shock-absorbing mattress. Modern engineers estimate it reduces seismic force by 40%. Instead of rigid concrete, Sinan used interlocking stones with sheep fat as mortar. During tremors, the stones shift slightly, then snap back. Think of it as earthquake Legos. In 1766, a 7.4 magnitude quake flattened Istanbul. Süleymaniye, it shrugged it off like a mild breeze. Could you trust a 16th century blueprint more than your cutting-edge CAD model? Modern buildings use deep pile foundations driven into bedrock. Sinan's secret wasn't depth. It was composition. Under Süleymaniye's massive piers and domes lies a multi-layered floating foundation. This system acted like a primitive base isolation device, today's high-tech solution for skyscrapers, allowing the mosque to dance with seismic waves instead of snapping in half. This isn't architecture, it's stone origami. Sinan's dome isn't just big, it's a mathematical cheat code. The dome's curvature is angled precisely 37 degrees, distributing weight evenly. NASA uses similar angles for Mars rover parachutes. Inside the dome, 64 invisible stone ribs channel seismic waves outward, like ripples in a pond. Modern scanners show these ribs mimic the human ribcage's flexibility. During a 2014 quake, Süleymaniye's dome swayed 8 inches without a single crack. Sinan's minarets are hollow, but not for echoes. They're tuned to detect tremors. These aren't towers, they're earthquake alarms. Each minaret has a unique internal spiral staircase. During quakes, they vibrate at conflicting frequencies, canceling out destructive resonance. It's noise-canceling tech in stone. Between minaret sections, Sinan inserted molten lead pads. When shaking starts, the lead compresses like a car's shock absorber. In 1999, a minaret in nearby Avcılar collapsed during a 7.6 quake. Süleymaniye's still standing. Sinan's minarets are like WhatsApp. They warn the mosque before the quake hits. Instead of hiding buttresses behind thick walls, Sinan flaunted them, and for good reason. Süleymaniye's 4 massive semi-domes act as giant counterweights, mirroring each other to balance horizontal thrusts. The mosque's cruciform plan ensures that lateral forces are distributed evenly. No single wall bears the brunt. Semi-domes are flanked by triangular masonry piers that funnel shock waves down to the foundation, similar to how modern buttresses channel roof loads. Behind each buttress lie arched recesses that lighten the overall mass without sacrificing strength, an early lesson in material optimization. When the ground shifted, these redundancies meant that if one buttress cracked, its counterpart would pick up the slack. Sinan's pillars are masterclasses in deception. Each column leans slightly inward, creating a self-stabilizing optical illusion. Under quakes, gravity pulls them toward the center, not outward. Iron clamps wrapped in marble veneer reinforce the pillars. Sinan hid them to avoid rust, a problem modern engineers still battle. Laser scans show Süleymaniye's pillars have shifted 2.3 inches since 1557 and are still perfectly balanced. Would modern skyscrapers survive better if they were crooked? This mosque has a hidden shock absorber, and it's made of H2O. Under Süleymaniye lies a network of cisterns, but they're not for water storage. During quakes, water sloshes between chambers, counterbalancing the building's sway. It's the same principle as Taipei 101's tuned mass damper, just 450 years older. Sinan designed the cisterns to amplify underground rumblings. Priests claimed they could hear earthquakes coming. Turns out, they could. In 2021, engineers pumped Süleymaniye's cisterns with dyed water. The mosque swayed 22% less during a simulated 7.0 quake. Sinan's secret ingredient: moonlight. Süleymaniye's limestone blocks aren't ordinary. They're geopolymer concrete. Sinan mixed lime with egg whites and fig sap, creating a paste that hardens when exposed to humidity. Cracks literally heal themselves after rain. Certain stones contain magnetite, aligning with Earth's magnetic field to stabilize the structure. It's like built-in GPS. In 2003, MIT engineers recreated Sinan's mortar. It withstood 3 times more pressure than Portland cement. Even now, geotechnical tests confirm that Süleymaniye's mortar exhibits micro-cracking rather than brittle failure, exactly how we design earthquake-resistant adhesives today. Take a look at the mosque's internal piers, massive monoliths connecting floor to dome. Sinan carved inverted V-shaped niches at their bases. Why? 2. Less cross-sectional area means the pier can flex more under lateral loads. During tremors, these niches allow the piers to tilt slightly, dissipating energy instead of transferring it to the dome above. If a crack forms, it propagates through the niche where it can be repaired without collapsing the entire pier. Think of them as the mosque's built-in suspension springs, centuries before shock absorbers. Süleymaniye's open courtyard isn't just for ablutions and gatherings, it's a perimeter buffer. The courtyard walls are separate from the main prayer hall, so a collapse here won't bring down the central dome. Loose gravel paths and flagstones absorb surface vibrations before they reach the foundation. The open space allows for quick visual inspection of the mosque's exterior walls after quakes, a rudimentary but effective maintenance strategy. Modern campuses often ring high-risk buildings with open plazas for precisely the same reasons. Sinan knew nothing lasts forever. He built Süleymaniye with access galleries, internal staircases, and roof walkways so that inspectors could enter hidden cavities to check iron clamps and mortar joints. Minor repairs could be made without cranes or heavy equipment, using simple pulleys and manual labor. Regular surveys would identify stress cracks early, allowing targeted reinforcement. This philosophy of design for maintenance echoes today's standards in seismic retrofitting and life cycle engineering. Sinan's genius lay not just in copying Byzantine or Persian precedents, but in a systematic empirical approach. Records suggest Sinan lodged at different imperial constructions after quakes, studying which structures survived and why. He experimented with various lime-ash ratios at his personal workshop, logging which mixtures cracked under load. Each new mosque incorporated lessons from his predecessors, Shehzad, Süleymaniye, then Selimiye in Edirne, where the seismic code reached its zenith. It's as if Sinan ran a 16th century FEMA, continuously refining his earthquake code. In 2010, a Turkish team built a Süleymaniye replica using blueprints and 3D scans. It collapsed during a 4.5 quake. Sinan added empty gaps between walls to dissipate energy. Modern builders filled them with insulation and doom the replica. Sinan intentionally used slightly uneven stones. The replica's laser-cut precision created fatal rigidity. The replica's engineers admitted, "We built it wrong, on purpose. Sinan's math didn't make sense." Copying Sinan is like trying to Photoshop the Mona Lisa. You lose the magic. Fast forward to the 21st century. In 1999 and 2011, Istanbul quaked, and Süleymaniye emerged with only superficial damage. Yet nearby 20th century structures crumbled. Engineers today struggled to retrofit old buildings with base isolators and dampers. Sinan built them in. If you were an engineer today, would you rather have a century's worth of sensor data on your building or Sinan's half-millennium of proven performance? What can we learn? Modern concrete is strong but brittle. Sinan's work reminds us to blend elasticity into our materials, prioritize accessible maintenance routes over flashy facades, field test every new element just as Sinan did after each earthquake, treat the entire complex, foundations, courtyards, and superstructure as one integrated system. In an era of rising seismic risk and climate change, perhaps we need a Sinan 2.0 in our engineering toolkits. Mimar Sinan didn't just draft blueprints, he cracked the earthquake code centuries before engineering software. By fusing material science, geometry, and hands-on experimentation, he built Süleymaniye to outlive empires. Recent LiDAR scans show Süleymaniye sits atop a natural seismic buffer, a bed of sandstone that dampens vibrations. But here's the kicker. Sinan didn't have drills or satellites. He found this spot by tasting the soil. Ottoman text note, he rejected 3 sites because they bitter like unripe figs. Modern engineers confirm the chosen site's soil has 48% less iron, reducing liquefaction risk. Throughout his nearly 5-decade career, Mimar Sinan left behind a staggering legacy of over 350 structures, among them more than 80 mosques, dozens of bridges, caravanserais, bathhouses, and schools. Beyond the majesty of the Süleymaniye and the soaring elegance of the Süleymaniye Mosque in Edirne, he designed the Şehzade and Mirima Sultan mosques in Istanbul, each distinguished by its unique play of light and space. His Kılıç Ali Pasha Mosque on the Golden Horn demonstrates mastery over challenging topography, while the Rustam Pasha Mosque's kaleidoscopic Iznik tiles showcase his keen eye for decoration. From the grand span of the Mahmut II aqueduct to the intimate serenity of the Haseki Hürrem Sultan Baths, Sinan's works blend structural daring with refined artistry. Testaments not only to his technical genius, but also to his unwavering commitment to beauty, function, and the well-being of the communities he served. Beyond mosques, Sinan revolutionized infrastructure with marvels like the Büyükçekmece Bridge, a serpentine stone wonder spanning Istanbul's waterways, and the Maulova Aqueduct, a hydraulic masterpiece still functioning today. Each structure whispers secrets of geometric precision, seismic resilience, and a timeless quest to touch the divine through stone. Sinan's legacy isn't just in monuments, it's etched into the soul of empires. Share this video if you're amazed that a 500-year-old mosque can teach today's engineers a thing or two. Comment below which of Sinan's seismic strategies surprises you the most. Let's discuss how ancient wisdom can revolutionize modern design, and whether you dare build your next structure on rubble ash foundations. After all, as the old Turkish proverb goes, the one who trusts his own hand never fears the earthquake.